Morning, morning, monsters. How's everyone doing this morning? We're going to do a part 2 of our scripting and graph logic talk, really. It's more a standalone talk about remote code execution and how we can power the metaverse. But obviously it's a follow-on from some of the previous stuff we chatted about graph logic versus scripting. And the conclusion to that talk is basically, from a tech point of view, either is fine. They both end up being very, very similar in execution. Execution, though, that is the tough problem. This is not something that's easy to retrofit to systems. This is architectural kind of low-level work that needs to be done. But what kind of work are we talking about, and why is it complicated? Well, the first thing you need to know is the speed of light exists. I know that sounds like such a silly thing, but unless we have some groundbreaking theoretical physics kind of crazy stuff, we are currently have to abide to the universal traffic limit of the speed of light. Yes, quantum entanglement has been demonstrated, but realistically, the application of that is far, far away. So what we really are talking about is speed of light. It's going to limit our communications, and we don't have to just talk from me to you and back, right? That's not just the round trip we're talking about. We're talking about hundreds of people potentially in a metaverse, if not thousands, if not higher concurrency. How do we handle that? And I can say this is probably the biggest unanswered question in the metaverse design at the moment. The thinking is throw money at it. We will figure it out eventually. Hope that the adoption curve is slow enough that we can come up with something. That's not to say we don't have strategies, and I'm going to talk about some of the strategies. I'm going to keep it relatively high level. So if you're a network programmer who has worked in this area or has dealt with this stuff, you might find some of the talk rudimentary, but for everyone else, it's really just an introduction. Right. So the first thing we need to talk about is this is really two separate problem spaces. The problem space of simulation, that is to say, figuring out what happens. So if I pick up this cup and I drink, that sound, how much the cup is drained, sound when I put it on the table, and then more importantly, my two hands clapping together. Collision, all that kind of stuff. Simulation, figuring out what happens next. If I had a little pot plant in my hand here, I've got one over there. If you saw a time lapse of it, it would be simulating the growth of that plant, whatever. All right. Simulation is figuring out what happens next. We have state A, we do a bunch of stuff, and we get state B. So it's a transformation. All right. And the other part of the problem is prediction. Right. This is in the absence of knowing what state B is, can we predict it with limited information? Okay. So, for example, I'm trying to think of something safe here. For example, the Sharpie, if I throw it up and I catch it, the path of the Sharpie, because no new forces are applied to it, we can predict the entire path of the Sharpie from the moment it leaves my hand, unless a new force is applied to it. But we don't know about any new forces or new interferences. So why are these two separate problems, and why are they both important? Well, the simple truth is that your simulation is at best running at 30 frames a second. Realistically, it's running a lot slower than that, or has to compensate for that in a bunch of ways, because let's stick local first. Let's say this is all running on your PC. Simulation's running at 30 frames a second, right? So your entire game logic thing is happening at that kind of speed. But the renderer for VR to look good is running a lot faster, let's say 120 frames. And so what we need to be able to do in the renderer is we need to be able to take what's happening and bring it forward a little bit. We need to take things like the animation system, audio playing, all kinds of things like that, and run it forward a little bit so we get a smoother experience. Very common, understandable problem that we solve all the time in game development. But that's because it's single player, and what we really talk about in the simulation space is trust. Okay, so what if we've got multiple people, all right, and we've got a simulation that involves different things. They're all talking, right? So imagine you've got a single computer and you've got 4 controllers plugged in. 2 of them are the really nice controllers, and then 2 of them are the janky third-party controllers that are a little bit slower, and you're playing a fighting game. The way the controller's working is we're checking who pushes X and punches first, right? But pressing X is not something you can anticipate. It's not like we know the controller's going to push X, right? So what we do is we're polling and we're figuring out when all the controllers are going to push X. That's not enough, because if there's any latency in any of the controllers, we can't really detect it. So what we need to do, instead of going from a raw, like watching a cable wire signal, we need to go to some kind of event-based or messaging protocol to figure out how old the signal is. Now, the simplest thing we could do is if every one of these controllers had a little clock in them, we could figure out the latency of all the controllers, right? But the problem is that player 4 is a bit of a slime ball, and they have tweaked their clock in their controller slightly so that any of their input looks like it is a little bit faster than it is, right? So basically they've slowed down their clock a little bit so that they can push X, and then when all those controller signals come in, we can go, oh, that person pushed X first, but they have a slower controller, right? And this is the kind of lag manipulation stuff that you see in multiplayer, and it's actually super common to the point where people will buy lag switches that they'll install, and they'll interfere with that kind of thing. The other thing you can do is you can send a round trip message, right? You can say, here's the kind of information, report back to me what you want to do in this frame, so we can all agree to move forward as one, right? We decide you get to push one button for this frame, and that's what we call lockstep. So the idea is that we're all moving forward, but we're moving forward in lockstep, right? Lockstep is nice and simple because there's no complexities to it. You'd be amazed at how many multiplayer games we can implement with lockstep. The problem with lockstep is that if one of the players has put down the controller or has unplugged the controller or whatever, or one of the players' controllers just occasionally glitches out and doesn't work, the entire simulation has to stop and kind of figure out, and everyone stutters, right? But now, before we go any further on the simulation side of this problem, let's talk about prediction. So lockstep, as we said, is one of those easier ways to do it, but we know we're now waiting for everyone to advance, right? But remember how I said with the prediction phase, well, logic's already running slower than the renderer, so we can kind of predict what people are doing. We can do similar thing with the lockstep logic. We can go, well, this is a car driving game. This is where people, they had their foot on the accelerator and stuff. Let's assume they keep on going, right? And so everything looks seamless to the user. And we've really come a far way in prediction. If you've played any of the old 90s netcode games where you would see players sort of stutter like this and then go boom, dum, 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 dum. Because what we'd be doing is we'd be predicting their motion forward for about, half a second, and then we're like, oh, the lockstep has locked up and we don't know where they're going, so let's just rewind them and try predict them forward. And that was our elegant solution. So we've got this problem of we're simulating, and then we're predicting where things are going forward, and predictions running faster than simulation. But then obviously the simulation, the lockstep happens, and the ground truth, the reality of what's happened has arrived, and so now we need to compensate for it. And we don't have time to go into all the different compensation methods, but the simplest example of this kind of compensation method is, let's say we're doing the driving game. We have predicted that they're here, but in reality they hit the brake and they turned, and so they're actually here. So how do we get them from here to here? Well, the honest truth is, in most cases we can kind of smear it over time, and we don't bring them straight there. No, we don't smear straight away. We correct over time, and that works for us, largely speaking. Okay, but now we have a problem, because while we were predicting that, another player was driving, and in our prediction the two players didn't hit, but in reality they did hit. And now you see where the networking problems start to occur. It's where we have collisions or impulse events. So a crash and crunch sound needed to be played. The reason why I emphasize the sound is your audio is usually running faster than your visual, and your audio is usually lower latency, and the human brain processes audio faster than it does visual signals. And we as game developers hack and abuse that fact, by the way, all the time. But in network code it really sucks, because it means we're expecting to hear a crunch and a crash, but we don't hear the crunch and the crash. So one solution is we can say, well, this player didn't think that they hit that car, therefore they didn't hit that car. So we can do this relative offset. So this is like if we were doing a first-person shooter, and we predicted the player was there, and the player pointed at where we predicted, and they pulled the trigger, and we'd say, well, that player thought they hit, so therefore they should hit. You can see where this is going. That's kind of problematic and can be abused because of some players zigzagging, but in the prediction they're not zigzagging because we couldn't predict the zig and the zag. Then they're easier to hit. But in other problems and things is, maybe that collision is super critical, and maybe the prediction is slightly different in different places. How do we resolve what people are dealing with? And now you're kind of getting into the headache space that we have. Now, going back to the simulation side of this question, the advantage of lockstep is we always have an authority, a ground truth that's moving forward, right? Whether the simulation is run on one of the peers or it's run on all of the peers, and we'll get to that, by the way. That's the difference between authoritative execution and execution everywhere, is one of the questions. But yeah, lockstep at least is nice, because we know going forward there's a ground truth we can rely on. So I diverged a little bit there, talking about execution, authoritative execution, and execution everywhere. So in a ideal world, you have a dedicated server that has the lowest possible latency to everyone, and all the server is doing is providing the authoritative execution, and the server is under your control, and no one can manipulate it. So while the different controllers I just spoke about may be plugged in, they're all plugged into a reliable machine. So we can go, this is the authority on what's happening. And that kind of works, and that's kind of nice. But one of the things it is very expensive. And the other thing you would say, some people say, is, well, if ever the server's running everything, that's great, because then the game clients don't need to do as much. The reality is the game clients usually have to do almost as much, if not the same work, because they have to predict. And to predict, they have to have an entire model of what's going to happen. This is actually what happens in our brains all the time, like when we throw balls and when we see projectiles, our brain is constantly predicting what's going to happen. So all the clients are hallucinating the future. And the human brain hallucinates the future all the time. It's very hackable. It's very interesting how we can do that. So yeah, execution in one place or execution everywhere. Now, one of the advantages of execution everywhere is this prediction thing I spoke about. But the other advantage is we can execute everywhere. So all the machines are running the simulation, but then we can do limited audit, and we can figure out when computers align to each other or when their simulations have mismatched. And we can have different strategies for dealing when they're mismatched, right? So for example, we can say to 3 computers, what is the result of this simulation? And if all computers agree, we go, great. If one of the computers disagree, then we're like, oh, maybe we nudge the simulation back, or maybe we start flagging them as hostile. Maybe we start auditing them more because they're getting suspicious. Or in the case of competitive games, maybe we focus more on the high-end players, the players that are winning, and we audit their results more. So there is strategies and methods as to how figuring out the audit, and when we find the discrepancies, we can nudge the correction. We can say, hey, actually the simulation not reliable in this case, and we can do that smearing thing I spoke about. Or we can basically go, oh, panic, desync, rewind. One of those things. So that's execution everywhere and server authoritative execution. I'm going over a lot of concepts here. There is a good reason for that, because I'm just trying to give you a taste of the kind of problems we're facing with the metaverse. Now, in both execution everywhere and authoritative execution, the issue is as we scale up the numbers of players, the work that either that one machine or every machine has to do is increasing, right, in complexity, and the latency is going up in all kinds of weird ways. So we need to come up with some strategies to mitigate that. To which we get to partial execution. Now, partial execution is very popular in PUBG, Battle Royale style games. And this is the situation where we have the map divided into sectors, say, and we say, well, you only need to get the network traffic of people nearby to you, and you only need to simulate the things that are happening near to you. Right, so we drastically reduce the scale of the problem. Now, there's some messy situations. What if all 100 people run into one spot and doing that stuff? And we have techniques of dealing with that where we throttle down the simulation speed, and we go lower resolution on the data, and we do all kinds of tricks and hacks like that. But essentially what we're doing is we're cutting up the map into grids, and we're saying we will send you any of the network traffic that is near to you, but overall you'll only be simulating the stuff around to you. And then when 2 players sort of start to come closer together, we then need to sync up their data. So this partial execution is really nice, though in answer to the question of if a tree falls down and no one's there to hear it, does it fall down? The answer is no, it doesn't. And we get into these weird problems where a simulation of a tree falling down might not have been happening because it was frozen, right? In video game worlds, designers often hack this away, so what we call offline execution never really happens. But let's say that we care because this is the metaverse, right? And so what we have is we have 2 buckets of water and 1 bucket's leaking into the other bucket. All the players run away, and no one's there to simulate the bucket tripping. Now, in theory, we could have the server pick up the occasional update tick from that bucket and say, well, no one simulated that bucket tick, so I'm going to simulate it authoritatively on a lower frequency. Or what we can do is, as players move about, in sort of a wider radius as it comes in. We can say, this thing hasn't been simulated for 3 minutes. Can you just run the simulation super fast for me and figure out where it should be? And that's a thing that some games in some cases do. There's a really good talk by, it's in a single player context, but the concepts apply in multiplayer. Noita, which is a pixel simulation game, where they do a similar thing, because it's a lot of off-screen simulation that happens there. But now the problem is, I talked about auditing and multiple points of execution because we can't trust. So do we trust that one player as to the state of the bucket? Maybe they lie to us and say gravity reversed. So in which case, we need a second player to run this. Or we have the authoritative server model. It's one of those tricky problems that we have to face. We've spoken about execution everywhere. We've spoken about auditing. We've spoken about partial execution. I think that covers all the independent execution models. Oh, no, there's one other futuristic one there. This is more for if you really want a broad metaverse. It is a form of server authoritative, and that is basically you can have a server authoritative model for, say, the wider world, but then you can have these smaller computers that have been spun up by the server, so they're authoritative, they're something you trust and control, and then you run small bits of execution. They like to decide, I'm going to simulate all the coffee cups and all the leaking buckets in the entire world, and that runs as a little background thing, and it is basically hyper optimized to deliver that result. And this is a interesting model that's been proposed by some people. I forget the name that some people have given it. In my head, I always think of it as the demon model, because it's I always think of the Matrix, and I always think of dedicated, like Unix demons. But the idea behind this is that if you have a machine that's dedicated to, say, I don't know, smoke simulation, and it is just crunching smoke simulations, and it's been hyper optimized to do smoke simulations by sending a smoke simulation and getting smoke simulations back, it is a way to improve the performance of that particular thing. In reality, the problem is that systems usually need to interact, and this causes issues because the smoke simulation sounds like a really simple dedicated thing, but then what about the physics simulation and the ball that's running through the physics simulation? And, is the smoke simulation responsible for the ball as it passes through the smoke simulation, or is the ball responsible, like the ball machine? So it does break down and stuff, but there are ways and means of applying this sort of hyper-focused model. It's kind of like microservices, but it's tricky. The problem is, as I say, we are trying to figure out how to scale up these models to large environments, because the kind of metaverses we're seeing at the moment are very sharded and small, and usually because of these problems. But let's get back to the prediction issue, right? So we've spoken about a lot of the different ways we can simulate. I haven't spoken about auditing that simulation. There is a bunch of different techniques. They go fairly deep. If you're interested in this kind of auditing, look for any good GDC talks on cheat or hacking detection, because this is usually where some of the best talks on this auditing and correction are. But there's a bunch of different ways. The simple truth is you don't need to worry about them too much at a high level, conceptual level. You basically think of, we need crypto, we need hash checks, we need these different techniques to basically verify execution in some way on partial execution models. So going back to prediction. Prediction. We've spoken about the simple physics case of sort of moving stuff forward or playing things forward. And remember how I sort of talked about the leaking bucket and the fast forwarding of that. The fast forwarding of that kind of thing is really useful, by the way, for prediction, because if you can run your this kind of stuff faster, it's there. We get into some tricky areas here, by the way, with floats and fast math functions. We know how to, on different computers and different hardware, run complicated floating point math in a reliable and deterministic way, regardless of hardware. The problem is it's dog slow. It's really, really slow. And to get the kind of performance, to get the kind of experience that everyone expects, especially for VR, we use what we call fast math functions. This is where we're approximating square roots. We're getting really loose and fast with what the floating point precision is. And we can make this usually predictable on one set of silicon. So like if it's a whole bunch of PS4s talking to a whole bunch of PS4s, they're all identical. Their errors are going to be very, very similar to the point where you as the average programmer don't worry about it. But the moment you have a PlayStation 4 talking to an Xbox, or a PlayStation 4 talking to a PC, or you just have different PCs talking to each other, that floating point prediction breaks down and gets us into all kinds of trouble. And also with prediction, we can sometimes get really fast and loose with the math. We can go, well, normally we simulate a time step of 120 frames a second, but we're just going to simulate this at 1 second and run it through. We get into some interesting problems there with physics models, because there's different ways. As an example, I'm going to just use physics. A whole bunch of stuff that breaks down when we do variable time step simulation, which is the fancy name for what I'm describing here. But for physics, we've got a simple thing of, if this Sharpie is going to hit this phone, right? We can say, oh, it hit the phone because we simulated it and it stepped forward and it's that much, and it's penetrating the phone, right? But if the Sharpie is moving fast enough, or if the simulation is running fast enough, we go, it's not hitting the phone, it's not hitting the phone, and it passes through. There's ways of solving this where we do basically a cast from one position to the other, but again, that's a little bit slower. So a lot of physics simulations run that sort of step process. And with it sounds, by the way, very simple to just do the raycast from here to here. And for static geometry, that works fine. But now the situation of, we have two pins, and do they collide in the interim or not, right? Between those two states. And the honest truth is, you have to do this really complicated solver math, or you just have to integrate and brute force it down. And in some cases we do the complicated math, and in some cases what we do is we're running this entire simulation, but we decide, because these things are so close to each other, we do an iterative solve, kind of like we do with path tracing and reducing spheres of nearest point to the sphere, nearest point to the line and stuff. We do all kinds of weird and fun hacks to figure this stuff out. But yeah, projection breakdown. So there's that. I've spoken about, with partial execution, I did kind of gloss over the fact that the syncing can fall out of state. Obviously with execution everywhere or server authoritative, you have to have kind of a knowledge of the entire state. With partial execution, because we're sharing this stuff, if two players are coming close together, we just have to tell about the results. We don't say all the things that led up to the current state. We just say, hey, I'm running, I'm currently on fire, and my left leg is missing. This is like my update. You don't need to know that it was a shark. You don't need to know that it was a nun throwing a Molotov cocktail after I ran off with her habit. You don't need to know why I'm in the state I'm in. You just need to know what state I'm in. And also with syncing in the metaverse, we can decide what's important and what's less important, and we can prioritize, right? So you may care that I'm on fire. You may care that my leg's missing, because these are immediately obvious things. But you might not care that I'm crying. Or you might not care that currently I'm wearing a red ring or a blue ring or whatever. Smaller details can come later, and that's actually how your brain kind of processes these things. And I think for the metaverse to work, we're gonna have to get comfortable with a weird form of deja vu and desync bugs, and we're gonna have to get comfortable with I think it's going to be one of these situations of traditional game developers are going to get really freaked out by metaverse coding, and are going to get really freaked out by trying to make everything perfect, because they're in like the Fortnite competitive shooter Valorant mindset. And you're going to have a whole bunch of VR kids and, you know, new age metaverse hippies like laughing at the glitching cat because it's been bumping into the wall for the last 5 seconds, right? So we're going to get, I think, a culture of design and a culture of players that are just kind of okay with the glitches. They're kind of okay with the fact that when someone walks into a room, it takes a second for their avatar to load in, or it looks like they have pink hair, but you haven't got their newest hair update, so then all of a sudden it flashes to red. We're going to get into this. I think we're going to get comfortable with these kind of glitches, and we're going to get comfortable with some people's IK, for example, running at a lower resolution because their bandwidth is not as good, or something like that. We're going to get comfortable with these smearing prediction effects that I'm talking about here. So that's, I think, one of the areas that we're going to see in a lot of this metaverse stuff, because at the moment, I think without exception, that from what I've seen, everyone is sharding quite heavily. I will say I do like Neos's mixed session model, where you can be in multiple sessions at a time. I think that's very forward thinking of them. It's something, it's not a new concept, but it's something they've implemented quite well. But yeah, so this has kind of been an overview of why this is a problem and why this is something we're spending a lot of time on. It becomes doubly hard when we're dealing with user-based execution, right? So if we're dealing with custom shaders, if we're dealing with custom graph logic or scripts that you have running, and again, I think Neos is ahead on the game on this than most other players, because in Neos I can run in and I can have all this complicated graphing stuff running on me, because I've decided that whenever my avatar touches my cheek, a little ooh sound plays, and you know, there's like a little heart particle thing that spawns off and all that kind of stuff, and that's stuff that I as a user have created, and we need to get comfortable with the scaling those kind of executions, having those kind of simulations bug out and halt on us and rewind. And I think that's honestly the only real way the metaverse is going to happen, unless someone solves weird quantum entanglement or these kind of crazy stuff. And what we're just going to do is, when you need that authority, when you decide you're in the metaverse and now we're going to play capture the flag or whatever, that's when you rope those people off into a smaller session. You say, okay, we're going into a server authoritative mode, we're going into an execute everywhere audit mode for this particular thing, and that's when we can lock it down. So I think we're going to have these lockdown performance bubbles for competitive or things where it really matters. But I think largely speaking, we're going to be in this quite messy space. Another place, by the way, where I think we're going to turn up into lockstep or into authoritative and going to turn down prediction is a situation where we're really close to, like me and you are very, very close, and we want to hug or we want to shake hands, or I just want to touch you there, and then it's like, oh, okay, now I really care where the person's hand is. And then actually when you're dealing with a peer-to-peer, like just two peers kind of situation, and you are like, this is an interaction where there's probably a high degree of trust, then you can do a lot of prediction models you wouldn't normally do, because you know that these players are probably want the highest fidelity that they can get. So that has been our sort of brief overview of remote execution and simulation and prediction problems. It's a round trip. It's a high level of all of this. Let's see if you all have anything to add. Ask away any questions and I'll try and answer them now. So I was pretty super fast. So I'm chasing you. Yeah. It's so that there are going to be weird. I think that's tangentially. I think there's going to be some weird situations with simulation bugs where people try to catch up to things, and I think there's going to be a lot of mind games. And yes, as Tricacia says, perfection is the enemy of good. But I do think it's a battle that we're going to fight, because I think it's not just developers that are going to have this problem. The issue is going to be that older gamers and more established gamers are going to see the jank, and I think they're going to say, well, oh, this netcode's terrible. They're going to sniff their nose up at it, and I think there's going to be a lot of kids these days don't know what good networking is, and not understanding the trade-offs that we're making, and the kind of experience. Because if it's a choice of, you can walk into a dance club and you can have 2,000 people there, right, and they're all experiencing this, but there's a bit of jank, or you have those same 2,000 people split off into 32-player, 64-player instances, whatever the smaller number is, right? All of a sudden you've gone from a shared single experience to these mirrored worlds that don't quite make the experience real, because which is the true dance club, right? Because that's how a lot of these bigger events work now at the moment with instancing. And were you in the instance where Gary ran onto stage and then was tackled by the goldfish in spandex? No, you weren't. Okay, so did that happen? Is that a story we can tell about? Quadfest 2022. Because it wasn't there. In fact, the only thing that's authoritative and actually happened in these events is the shared Twitch stream or the shared video or music stream. And that, I think, takes away, it's like, oh, actually it's 100 different private parties. And the thing that you were attending was actually just a small house party. You weren't at an event of 2,000 people. So when we do talk about these large scale events and we say, oh, it was attended by 1 million people concurrently, it's like, was it really though? What you're more saying is 1 million people watched a TV show, right? So to get to these large scale events, and to have things where we can all talk about the goldfish and spandex, then we need to move to a world where maybe some people saw the goldfish ever so slightly differently, but hey, reality is not perfect. If you asked for 100 eyewitness accounts, you would get very, very different results, and I think we can embrace that. That being said, folks, I think that is our chat for today. I hasten to add, by the way, if you haven't seen it, I set up a new YouTube channel for my skating. It's Skate Southwark. And for April, I'm going to be skating every single day, and there's going to be videos up there every single day. It's a challenge I've done a few times before, to skate every day in a month. I really enjoy it. It'll just get me out and to enjoy the sun, because obviously I've been in winter hibernation mode with all the lockdown and everything. So if you like skating at all, or if you just like to see some silliness, those will be going up. But I have put them on a separate channel just so other people who are not interested in all my skate videos won't be bombarded with 30, 31. How many days in April? I should have checked before I started the challenge. How many days in April? Let's find out. 30 days. 30 days in April. My 30 skate videos just bombarding it. Okay. That being said, take care, everyone, and I will see you when I see you. Bye-bye.